Hello everyone and welcome to today's session. I thank each one of you for gracing this exciting event and showing your enthusiasm towards space and Stardour. Myself Dhanush, I am the co-founder and chief operating officer at Stardour. Before we move on, first of all, I would like to congratulate the entire team of ISRO for a successful mission of PSLV C-52 that was launched today early morning at 6:17 from Satish Dhawan Space Center, Sriharikota, carrying Earth observation satellite EOS-4 into sun-synchronous polar orbit. It is so good to have a webinar today. We have Mr. Sankash, my co-founder and director. He is also the founder and chairman of Savard, an investment advisory company. Now let me introduce my team who are going to be the speakers to this webinar, including myself. Firstly, I welcome Mr. Ravindranath. He is the Chief Executive Officer and Head of Research and Development. Next is Mr. Sharan Roy, Propulsion Engineer. And then we have Mr. Vivek Satish, Flight Dynamics and Controls Engineer. And all the speakers are joining this beautiful event from different parts of the country. Before I begin, for those of you just joining us, welcome. I once again appreciate everyone for spending your time with Stardour. Let me begin by telling you this. Why would someone climb Mount Everest? Why would someone sits on desk with pen and paper and tries to understand the nature? Why would someone tries to explore things in space? Why would someone tries to build human habitable space station? Why did Soviet Union launched Sputnik in 1957? Why did the Yuri Gagarin become the first man to enter deep space in 1961? Under Apollo program in 1969, why did United States send astronauts Neil Armstrong and Buzz Aldrin to moon and returned back them safely to Earth? And now, why NASA is going back to the moon under Artemis program? And now why SpaceX is aiming at Mars? It is absolutely not to show their technological superiority, and it is utterly not because of some other reasons other than human curiosity. Human curiosity drives humanity. And that's where actually the name Stardour comes. It is an hybrid name, comes from two words, star and order. So jointly as Stardour, which represents enthusiasm and curiosity towards the vast cosmos. And we are based in Hyderabad, India. Our perseverance is to perform all kinds of aerospace activities in the vicinity of reachable lands, water bodies, and deep spaces in space. And we do this by designing, manufacturing, and operating the aerospace programs with the world's most ridiculously advanced ingenious launch vehicle called Rendezvous. Before we gaze and discuss Rendezvous, I may request Mr. Ravindranath, Chief Executive Officer, to deliver some more ideas and concepts of Stardour. Sir, can you please unmute your mic?
Yeah, good morning, everybody. Yeah, yes, sorry for the disturbance. Yeah, good morning, everybody. Echo is okay, fine. Yeah. Yeah, as Tanusha told, space is actually a place where people are really very much enthused actually. The exploration on for space, this thing, space exploration, and then the cosmos really is a thing which really made a human man wonder about it, and then the exploration. Yeah, coming to this, space sector was actually dominated by the public sectors in the government agencies all over the world, and then it was a monopoly of government organizations, basically. And there were a lot of regulations and compliances which really hindered the progress of it very quickly. Now, after the first launch of the Sputnik and then man to the moon in '69, the progress was quite good, but it was not at the pace what it should have been. Once the things have moved to the private sector, like SpaceX, Blue Origin, Virgin Galactic, and then now in India also, when the space is open to the private sector, things are moving very quickly. And in the progress, we can see that it is moving very, very fast pace. This we have observed in other industries too, like telecom and all. We have seen a lot of innovations taking place once the private sector has stepped in. Like in telecom, if you see, when the equipment manufacturing and all was privatized in India, we have seen that the cost of the equipment has come down drastically, and then a lot of innovation has taken place. And when the spectrum was opened, the cost of data, the cost of voice call, everything has come down, and then the reach also. It has reached to the general public, and then it has become affordable to the common man. Similarly, we from Stardour want to make space affordable to the common people, and then we want to make it a commodity-like thing. And then our vision, unlike others who are aiming to just say go to moon or Mars or anything, something like that, or space tourism, our vision is quite different one. It is something like having a ocean liner, a space liner like thing, which actually brings in a development where the entire space will be available for people to move around, and then we can aim for interplanetary travel too. Our vision is to make space colonies orbiting around planets, Earth, Moon, and other planets, and then we will be having space liners moving in between these orbiting stations, and then we'll be having launch shuttle services between the planet and to the orbiting stations, and then of course the space liners will be moving around the planets in between the planets, like ocean freight, ocean liners and ocean freight carriers. This is our main vision, and then for achieving these things, we need to start developing our own engines, our own vehicles, and our program for that will be elaborated by our subsequent speakers like Sharan and then Vivek, and also Then they'll be taking it forward.
Yeah, thank you. Yeah, well, yes. So basically, it is our proprietary technology. It is a two-stage, fully reusable space plane. I repeat, it is a two-stage, fully reusable space plane comprising of a carrier called Vagabond and an orbiter called Pursuit. Let me show you the larger scale of it. So yeah, let me make a point on the major objectives that are responsible for making us to conceive and come up with this type of unconventional launch vehicle system. Yes, the first objective was reusability of launch vehicle. Spacecrafts take huge amount of money to manufacture, and upon a successful mission, we cannot see them burning up in air or crashing on land or into water bodies. And if it happens, then again we must go for investing time and money for producing the next vehicle. And hence it is definitely not going to be an affordable job to work with rockets. And so reusability becomes very much essential for lowering down the budgets and time between any two subsequent missions. The second objective was making the land as well as water bodies as the launch and landing pads. The reason we also make use water as a launch pad is because in some trajectories, the re-entered carrier or orbiter may not end their journeys at the place they were launched. In most cases, they will end up their journeys on water bodies because 70% of Earth is covered with water. That is why we see space capsules, boosters heading towards oceans. And to serve these both objectives, our vehicle took this shape and came to life here at Stardour. In fact, we realized that this rendezvous is not just famous for reusability and as an amphibian vehicle, but it has got incredible number of advantages. Before I discuss, let me stress on a point. In summary, this is what we have created. A two-stage, fully reusable launch vehicle that can take off and land on both the ground and water for any kind of space program. And we are proud to say that Starter is the India's first private space company developing fully reusable launch vehicle, and it is the only private space company in the world to adopt the idea of performing takeoffs and landings on both ground as well as on the water bodies. Now, moving to the advantages of Rendezvous, it can be briefed out in 12 points. Here you go. The first is reusability. Both the stages of Rendezvous, Vagabond and Pursuit are fully reusable vehicles. Second is multi-mission vehicle. Actually, we are going to have three different types of Rendezvous configurations with different payload capacities. The higher configurations of Pursuit can be placed in parking orbit, and then it can be refueled and maneuvered to higher orbit or even to Moon, Mars, and even deep space. All this can be done using Rendezvous. The third is aerodynamic stability. The aerodynamic structure allows both Vagabond and Pursuit to move at high speeds and has more controllability in stage separation phase, in re-entry phase, as well as while landing. The fourth is takeoff and landing. As I said earlier, takeoff and landing can be done on water and land. So it has got facility in global reach. The fifth is very important, fuel consumption. Fuel is not necessary for bringing back and landing Vagabond or Pursuit. Whereas in vertical landings, fuel is compulsory for propulsive landing, for reducing vehicle speed and keeping vehicle vertical while landing. Which means at the time of takeoff itself, we must carry fuel. But that will again add takeoff mass, which is not a good idea. So in Rendezvous case, just by taking the advantage of gravitational pull and aerodynamic structure, the vehicle can be brought down like space shuttle. And the sixth is payload configuration. There are three configurations of Rendezvous: Rendezvous 1, Rendezvous 2, and Rendezvous 3. Rendezvous 1 is having payload capacity of 100 kgs. Rendezvous 2 is having payload capacity of 1500 kgs. And Rendezvous 3 is having payload capacity of 4000 kgs. All these are great enough to perform all kinds of space activities. And the seventh is spacecraft and aircraft. Here, Vagabond and Pursuit can behave like a spacecraft as well as an aircraft. And eighth is mission preparation period. A minimum time and effort is sufficient for planning the mission, as the same configuration holds in all vehicles with the different capacities. And the ninth is testing. It is easy to test due to simple and conventional technology, whereas in vertical landing systems, lots of testings are required for accurate thrust vectoring. But whereas in this case, it is pretty much easier. And the tenth advantage is a scope of success. It is obviously very much affordable, feasible, accessible, and it is a reliable technology. And the 11th one we have is maintenance of runway. Maintaining and operating of runway are very much easier compared to conventional launch pads. Whereas in conventional launch pads, it is something like a factory. We have launched our launch pad, so it's very difficult to operate all these things. Whereas coming to the runway, it is pretty much easier. And the last point is technical effort. The effort and time to be deployed between subsequent missions is very much minimal due to low maintenance demands compared to conventional launch vehicle system. So these are the advantages of Rendezvous. Yeah. Now I may request Mr. Sharan Roy, propulsion engineer, to deliver the concept of a propulsion. We are working on it. That we are working on it.
Yeah, thanks, Dhanush. Yeah, so my name is Sharan. I'm the propulsion engineer here at Stardour. I'm one of the propulsion engineers here at Stardour. Just give me a few seconds. Let me just try to upload the presentation. Just give me a moment.
Yes, Sharon, we can see your slides.
Oh, okay. I think it's still loading on my end a little bit. I'm still not able to see my slides. Actually, I'll go ahead and share my screen in that case.
Yeah, that will be better rather than use in PowerPoint Live.
Okay, hope everyone can see my screen now.
Yes.
Okay. Yeah, so good afternoon, everybody. My name is Sharan. I'm the propulsion, like one of the propulsion engineers here at Stardour. So yeah, like Dhanush said, I'll walk you through a little bit of the technical details of what challenges we face, especially in the propulsion front, and how we're trying to tackle them, and like how we're trying to make something new and revolutionary. So we'll start with a little bit of theory. I hope I won't bore you a little bit too much. We'll start with what exactly is the aim of a propulsion system in general, especially when considering launch vehicles. So the main aim of a propulsion system in launch vehicles is to deliver a payload at a high velocity, or basically this in the industry is known as delta V. So each mission requires a certain amount of velocity that you need to impart to a payload. For example, if you want to do a low Earth orbit, you actually have to give a velocity of 7.5 kilometer per second. If you want to escape out of Earth, it's around 11.5 kilometer per second. So once we know kind of the mission and like what mission we want to do and what payload we are carrying, we kind of can start estimating the size of the vehicle as well as like what propulsion needs are required. Vivek will actually go through a little bit about the sizing, about how we selected this payload and, as well as the mission. But let's consider that this has already been selected, like the payload and the mission as well. So once we have that, we actually move into the rocket equation, which gives an estimate of what kind of propulsion system that we need. Now, it looks like a complicated equation, but if you look at it in terms of like each term, it becomes much more simpler. The first one on the left-hand side is the delta V. This is what the mission requires. So like I said, for low Earth orbit, you might require 7.5 kilometers per second. That's what we plug in over here on the left-hand side. On the right-hand side is like the balancing aspect of it. What exactly are we providing and where exactly are the losses happening? So obviously our fuel as well as the engine basically provides the thrust for this vehicle, and that's what is giving you that acceleration or that delta V finally. So that first term is basically a combination of the fuel as well as the engine that we're using. The next term over here is, as you see, it's a negative term. It's a gravity loss. The easiest way to understand this is if you imagine a vehicle that is suspended or that is hovering, that requires a little bit of fuel to like remain in that hovering position. Otherwise, it would fall. So this amount of fuel that you're using for basically hovering, that's basically gravity loss. So as you're ascending the atmosphere, you're actually fighting against the gravity, and therefore you're going to incur a little bit of loss over here. And as you see, this TB term, that's basically your burn time. So longer amount of time you take to reach your orbit, that's where you're going to have more gravity loss. Similarly, you also have this next term, which is basically drag. So aerodynamic drag mainly depends on the shape and size of the vehicle. So bigger the size of the vehicle, or if it's poorly designed, then you have this higher amount of drag that this vehicle will be facing. So that's another challenge that we'll need to look into. And then finally, you have miscellaneous kinds of losses. Basically, if you are steering the vehicle or if there is any orbital maneuvers performed or any other losses, then you have this kind of losses, like extra bits of losses. So as you see, like all of these losses that are coming, they're basically being removed from the fuel and engine side. So our main mission from propulsion side is to increase this propulsion contribution as much as possible. So that's that first term over there. Well, how exactly do we increase this propulsion contribution? So if you look at it pretty simply, G is a constant, it's gravitational constant. So technically we are dealing with only two terms over here. We look at this M0 by MF. This in the industry is known as mass ratio, or basically your initial mass to your final mass. So we can increase that number for sure, and then we can try to increase your propulsion contribution. But the problem is when you're trying to increase this number, you're increasing the amount of propellant that you're using. And essentially what that means is you're increasing the size of your vehicle, you're increasing the drag on the vehicle, you're using more propellant. And because the vehicle is now heavier, you need to have more thrust, which means bigger engines. Ultimately, all of this accounts to larger cost, which is not something that we want. The other way is to increase this ISP part of it. ISP simply is a specific impulse, or basically it's how you measure efficiency of a rocket engine. Basically, that means if you're having more thrust for less amount of propellant, you're increasing a specific impulse. So to summarize, the aim of a propulsion system is mainly to increase the specific impulse as much as possible. So with a more efficient engine, you're obviously going to get much more benefits. Just a little bit more theory, specific impulse, you just present it in this kind of equation where it's basically thrust divided propellant weight flow. It's similar to how you think about mileage in a car. It's how many kilometers you take per liter. This is something similar, whereas you're looking at how much thrust per propellant weight flow. Now, if you look at the kinds of engines that we have currently, you'll see a kind of a trend over here. And where rocket engines are placed is actually very dead last. So you have the specific impulse of a rocket engine is around 300, 350, 400 seconds, which is actually poor performance compared to other engines that you see. So for example, if you look at turbofan engines, these are engines that you use in commercial airplanes. These go from 3000 to around 8000 seconds of thrust, which is, seconds of specific impulse, which is around 10 to 20 times much more efficient than a rocket engine. And that is mainly because whereas a rocket engine will have to carry a fuel and oxidizer because it travels in space. Any airline engine basically doesn't need to carry its own air. You're getting that air from the atmosphere itself. And only thing you need to carry is your fuel. So that's why they actually become much more efficient. And then as you see, you have fighter jets and ramjets, scramjets with lowering specific impulse, but still much higher than rocket. So the one thing that we need to note here is we need to try to figure out some way to actually get harness this benefit of turbofans while also making a like a spacecraft like that what we are aiming for. Now you might ask, aren't there any other engines that work in space? There are. You might have heard of solar kind of solar propulsion or ionic propulsion, plasma propulsion, electrical propulsion. Well, you have all this propulsion, but the main drawback is the thrust levels that they're setting or that they're giving is only maybe 10 kgs or 100 kgs max. Whereas for a rocket, you need in tons. And so chemical energy or chemical kind of propulsion that you see in daily rockets these days, that's the only kind of way that we can do this. So we are limited by what kind of engines we need. So regardless of whatever we look at, we need rocket engines for sure for taking us into space. But again, our main aim is trying to see if we can harness this turbofan as, also. And that is where Stardour, at Stardour, we're trying to look into a hybrid propulsion concept. So like Dhanush said, this is what our vehicle is Rendezvous. It's a two-stage to orbit vehicle. So what we propose is like for the first stage, which is known as Vagabond, which is like the booster stage, we split it into two phases. So the first phase is a jet propulsion horizontal takeoff. So this is something like how your regular airliners work, how regular commercial aircraft work, where you're using jet engines to take off from a runway at a pretty slow rate. You're always going to be in the subsonic regime and you're going to climb as fast as possible to 15-kilometer altitude, which is like the upper limit of what jet propulsion, where you can use jet propulsion. As soon as we reach that altitude, we do a rapid ascent, a quick ascent using rocket propulsion. So we have a rocket propulsion elements also within the same vehicle. And this will push it to supersonic regime and will climb to a predetermined altitude that is determined by the mission. Once we reach this altitude, we do a separation where the second stage separates, second stage being pursuit. And then finally, you have the Vagabond, which returns back to its back to the spaceport or what, like the runway that it launched from. And since we are using jet propulsion in this spacecraft, we can actually do a propelled or like we can do a um, we can use propulsion systems as well, jet propulsion system as well, to actually come and land back into the airport. Whereas the carrier stage, which is the second stage, the pursuit, that goes all the way to orbit, to whatever orbit that we desire, and will also accelerate the payload to the correct delta V that we need. And once it establishes that mission, we can also return this pursuit vehicle also back to the same runway, and thus achieve basically horizontal takeoff and horizontal landing. So what exactly are the disadvantages and advantages? I'll start with disadvantages. One clear one is that you have a combined system. You have jet propulsion as well as rocket propulsion. So obviously you're carrying a little bit more inert weight. You're also increasing complexity and maybe a little bit of fixed costs. But having this kind of hybrid propulsion system actually has a lot more advantages. For one, like I said, you have higher ISP for that initial climb, which is, like I said, jet engines are about 10 to 15 to 20 times as much more efficient than rocket engines. So you're going to get, you have to carry a lot less fuel and lot less oxidizer for launching this vehicle. And because you're carrying this less amount of propellant, you also decrease the size of the vehicle. And when you're decreasing size, like I said, your drag also decreases, which makes it much more efficient. You're reducing your drag losses. And then finally, if you look at into this drag term, like I said, this area is basically how you're reducing this size of the vehicle. But we are also doing another way of reducing drag losses. Conventional rockets will push as fast as possible from the Earth itself, which means you're having high velocity in a high density atmosphere. So both these terms are very high, which means your drag, especially in the initial phase, is very high for conventional rockets. So you're having a lot of loss. Whereas in our case, what we are doing is we are having this jet engine takeoff, which means we are taking off at a low velocity in a high density atmosphere, which means we are actually reducing this drag losses by a lot. And once we cross this upper bounds of atmosphere where you have much thinner air, little bit less density, that is when we do rocket propulsion. So we are increasing the velocity faster. So we are always balancing this drag to keep it as minimal as possible. So that has a huge advantage. And finally, because we are deploying this rocket engine at a very high altitude, we actually can use a vacuum optimized engine. So for those who are a little bit more, who understand a little bit into rocket propulsion technology, like you would understand there's a difference between vacuum optimized and sea level optimized engines. Whereas sea level optimized, where the difference between these two engines, you have a ISP of like 40 seconds difference, which in rocket terms, it's a huge amount of savings actually. So because we are deploying at a very high altitude, you're actually having higher efficiency rocket engines. And that will, again, reduce our propellant even more and reduce the complexity also even more. So how far have we come? So we are currently developing the rocket engine part of it. And so the rocket engine is known as the Hermes engine. So Hermes engine is a small thrust liquid rocket engine. It's around 30 kilonewtons of thrust. We're planning on using RP1 and LOX as our main propellants. This has been a well-established propellant combination. We are planning on looking into electric pump fed cycle, which is actually very suitable for small scale engines such as ours right here. And it's one of the newer technology which also gives higher performance gains actually. And like I said, it's also a vacuum optimized engine, which is why you see this huge bell-shaped nozzle, um, which also gives you finally a higher target specific impulse of around 300, 340 seconds of 346 seconds of ISP. Um, Finally, looking into what what our future at propulsion is right now. So we're currently at the preliminary design phase. We're actually wrapping up most of our design. Once we're done with this design, we're looking into rapid prototyping of small components. And these small prototype components, we're planning on doing component level testing and then again, re-prototyping and doing a lot more component level testing. Once we finalize this design, we move into manufacturing phase, where we're trying to look into like exotic materials if possible for our engine, which can make it more lighter as well as. And finally, once we have this engine, we are going to look into cold and hot fire tests. We are going to test the operational limits of our engine, going to see how long it can sustain its burn and how much reusable our engine is finally going to be. And finally, we'll look into packaging and system integration. So like integrating this into our airframe and then seeing how it performs with a couple of demonstrator missions. And obviously, there is always an iterative cycle that comes in between. So like at any stage, if we find that it's not operating up to standards or if there is inefficiencies, then we'll again reiterate this cycle and then try to make as best of an engine as possible. So that's basically from propulsion side. Yeah, so I'll hand it over to Vivek, who'll go into a little bit more into the mission as well as like the sizing and sizing aspects as well as the mission as well as like more into the mission aspects. Yeah.
Yes, thank you, Sharon. That was amazing explanation. Now I may request Mr. Vivek Satish, Flight Dynamics and Controls Engineer, to speak.
So hi everyone, good afternoon. Is the slides visible?
Yes.
Okay, so myself Vivek Sadish. So I'm the flight dynamics engineer here at Stardour. So today I would like to give you all an overview of the launch vehicle Rendezvous, which is currently under development here in Stardour. So like Dhanush has already mentioned, like Rendezvous is a like two-stage to orbit vehicle which is completely reusable, and it is having a winged configuration, and it's capable of horizontal takeoff as well as horizontal landing. So the first stage, it's called Vagabond, and the second stage it's called Pursuit. So like first, I would like to discuss about like how we came up with this configuration. So like if you look into space transportation system design, like we have like different configurations like expendable rockets, vertical takeoff, vertical landing cases, vertical takeoff, horizontal landing cases, and the one we have chosen, that is horizontal takeoff and horizontal landing. So like out of all these configurations, like why horizontal takeoff, horizontal landing? So that's the first question I would like to answer. So basically, like if you look into the space transportation system requirements, the main objective is to like increase the payload capacity while you minimize the vehicle mass. So along with it, like there are like some other requirements which we need to like consider. So whether it is reusable. So if you look at the space plane concept, yeah, obviously it is reusable because it's having an aircraft kind of operation. So once the vehicle is reusable, you can like increase the launch frequency. So increasing the launch frequency means like obviously it's going to be affordable. So coming to the reliability, flexibility, infrastructure part, like as I already like told you that as we are having aircraft kind of operation, certainly it's reliable. And coming to the flexibility part, yeah, like we can handle multiple missions. And coming to the infrastructure part, we don't require expensive launch pads in our case. So you can see that like if you compare all these aspects, you can see that the spaceplane concepts fares better in all these aspects. So like there is a question like even though like spaceplane is a superior design compared to the other configurations, like why don't we have spaceplanes as of now? So the answer to the question is the development cost. Because of the high development cost, right now we are not having spaceplanes. So, but looking at the present, we can see that like we are at a better stage. We have better technology, and we have like considerably reduced the weight of satellites which are to be launched. And because of the emerging markets for this small launch vehicles, now like we can like build smaller like space planes. So like we can like reduce the development cost as well as the development time. So, okay, so coming to the like design of any space transportation system, the first thing what we have to decide is the orbital mission requirements, like uh, the mass of the payload which we need to like carry to the orbit, and like which orbit we need to like take the satellite. So for that, like the like design team, like first what we did was a market study. So like we analyzed the market for the small satellite launch vehicles, and you can see like two figures here, like one shows the like demand forecast for like small satellites in the coming year, and if you look at the other figure, you can see the orbital requirements of these satellites. So from the like market study, the major market gap what we could identify was that like right now we don't have many dedicated small satellite launch vehicles. So right now, like what is usually done is like you carry the small satellites along with the heavier payloads. So if you look at the today's launch of ESL, you can see that the main payload was a radar imaging satellite, and you can see that along with that, two small satellites were also carried along with it. So the problem here is that like if you want to like launch small satellites, you have to wait till there is a major launch, like a heavier launch, which is to be carried to the orbit. So to address this market gap, we have decided that Rendezvous will be a reusable small left launch vehicle for like specifically for Earth orbit missions, and it will be capable of carrying 100 kilograms to sun synchronous orbit of 500 kilometer, and it has the capacity to take 160 kilograms to low Earth orbit of 200 kilograms and a 45-degree inclination. So in the table, you can see that like I have like listed down similar launch like small lift launch vehicles, and out of all these launch vehicles, you can see that Rendezvous is the only vehicle which is fully reusable. So fully reusable means like you can increase the flight frequency, thus like bringing in the cost effectiveness factors compared to the other vehicles. So like once the mission requirement is fixed, like the orbital requirements is fixed, the next phase of the design is to like fix on the mission profile. So like as Sharon has already like explained in detail the mission profile, like I would like to I'll just highlight the difference between the mission profile of a conventional rocket as well as the space plane. So if you look into the conventional rocket, expendable rockets, you can see that the mission profile is entirely different than that of like space plane. So in conventional rockets, the main objective is to like escape the atmosphere as soon as possible. So like it's a critical factor. Like within the atmosphere, the launch vehicle is subjected to very high loads like instabilities. So you design the trajectory such that you escape the atmosphere as soon as possible. So usually like it's vertical takeoff. After the vertical takeoff, they maintain a single zero angle of attack trajectory once till it like crosses the atmosphere. So once the atmosphere is crossed, then the launch vehicle is like steered into an optimal launch direction until like you get the orbital injection. So coming to the like our like space plane concept, like we have like an entirely different mission profile, like where the like launch vehicle, that is Vagabond, along with carrying the pursuit, will be taking off conventionally from conventional airport, and it will be climbing to the like desired final orbit as like explained by Sharon. So like you can see that like for a space plane, I have written the rocket equations here. So the basic difference between the expendable rocket and space plane is that like here in the spaceplane concept, we are adding orbital velocity in 3 stages. So you can see that like there is a air breathing stage here, then you have the Vagabond booster stage, and you have the pursuit booster stage. So if you look at a two-stage conventional rocket, you only have like 2 rocket stages to like impart the orbital velocity. But coming to the spaceplane concept, like you are able to add the required, means a part of the required orbital velocity more efficiently and effectively, like utilizing the atmosphere in the spaceplane concept. So this is like certainly giving us the advantage in the terms of like fuel efficiency when compared to the expendable rockets. Now, like once the mission requirements and the mission constraint is fixed, then like the objective is to like design an optimum trajectory. So like when you're like designing an optimum trajectory, you have to take into consideration a lot of constraints, like which are like put forward by the different subsystems. So like if you look into the mission requirements, the mission requirements fixes the performance requirements. So once the performance requirements is fixed, then that will decide the propulsion system design. So on a similar note, if you look at structures, structural design depends on the load. So the load like depends on the flight environment and also the aerodynamic characteristics as well as the like trajectory design. So if you look deep into the trajectory design, like the different mission profile phases, like we have an atmospheric flight phase, we have stage separation, we have re-entry phase. So each of these phases put forward like a lot of other critical challenges. For example, if you look into the atmospheric flight phase, then like we have limitations on the like maximum acceleration what we can like subject the vehicle to. We have like limitations on the maximum dynamic pressure. And another critical challenge what we are trying to solve is to like reduce the transonic drag, especially with the carrying pursuit over Vagabond. So these are like critical issues we need to like solve. And coming to the stage separation part, again, fixing the staging altitude as well as the staging bank number is one like critical issue what we need to solve, because this influences the sizing of the Vagabond as well as pursuit. So coming to the re-entry phase again, like as we are like entering the atmosphere, like high speeds, there will be like loads due to the deceleration, and like there will be aerodynamic heating, and you can see that like there will be changes in the stability characteristics once we are like doing the re-entry phase. And like one of the main requirement of our pursuit is that like it should be able to glide back to the launch site. So this put forwards requirements for the lift to drag ratio. So you can see that like all this like different requirements will change the trajectory design. So based on the input from the trajectory design, you do the navigation, guidance, and control design. So any changes in the trajectory design is going to give a change in the navigation, guidance, control design, as well as it's going to change the propulsion system design, which again like puts limitations on the performance requirement. So you can see that like it's a loop. There is like close interaction between all the subsystems. So you can see that like mission design is an iterative procedure until we reach the optimum design for our vehicle. So right now, like here at Stardour, we are like carrying out detailed mission studies to come up with the optimum design for Rendezvous. So that's all from the like mission design team. So thank you everyone for your time. Now like Danish can like take over.
Yes, thank you, Vivek. That was a nice presentation. All right, everyone. This is all we are having. Now we are open for a Q&A session. I request you can please raise your hands if you're having any questions, and we are happy to answer. All right, I think participants are not having any questions. Everything got cleared from this, whatever we have spoken till now. That's all for this webinar. I once again thank each and everyone for spending your time with Stardour. So, Mr. Ravindra, you have anything yet to speak? Okay, fine. All right, guys. Bye, everyone.